Greetings. So welcome to this session. So having learned the process or the Bode diagram of the individual factors and the process of constructing them, let's apply a simple. Let's apply the concepts to a simple example and learn how do we construct the Bode plot of any given transfer function. And we will make some interesting observations from this example, which will also be useful going forward, right? So let's consider a transfer function of the form. Let's say we have a plant whose transfer function is of the form s by s plus 1 divided by s plus 10, right? So we can immediately observe that the value of n is 1, the value of m is 1, there is 1 0 at minus 1, okay, 1 pole at minus 10, right? So we can immediately make these observations, right? So now the question is to construct the Bode plot, right? So for this particular transfer function, how do we do it? So let's look at this. So what we do is the following: we decompose in the standard form, right, that we have learned. See, what are the standard forms that we have learned? We have essentially learned a constant k, 1 by s, s, 1 by ts plus 1, ts plus 1, and the second order factors, right? Here we don't have second order factors, right? And neither do we have integrators and derivative terms. Yeah, right? Do we? So we have only first order factors. But then we need to put them in the form ts plus 1 and 1 by ts plus 1. Please note that we will have k ts plus 1 and 1 by ts plus 1. All right? So we need to put it in these three factors. These three factors are the relevant ones in this particular problem, right? I hope it's clear how we got it. But then please note that in the numerator, although the constant term is 1, in the denominator, we have a constant term which is 10. So the first step for us is to make the term of the constant in the denominator to be 1. So how can we do this? Let us say we take 10 out of the term, all right, in the denominator. So I can write the denominator as 10 times s by 10 plus 1. I think all of us can immediately agree to this point, right? How I did this. So why did I do this? I wanted to make this constant term as 1, right? So that's why we pulled 10 out of the factor, right? And then like we wrote it in this term. So now we can have 1 by 10. I will write it as 0.1. And then we have s plus 1. And then divided by 0.1 s plus 1, right? I hope it is clear how we got this sort of structure, right? By doing a simple algebraic manipulation, right? So we have not done anything major. It's a very simple algebraic manipulation, and we have got the structure. So immediately we can observe that this can be written as a product of three terms: 0.1, s plus 1, and 1 divided by 0.1 plus s plus 1. Okay. So we can immediately see that these are the three terms that we want to do. So the first term is this constant k, which in this case is 0.1. The second term is this factor s plus 1, which is of the form ts plus 1. And the third term is 1 divided by 0.1 s plus 1, which is of the form 1 by ts. All right. So I hope it is clear how we got these three terms. All right. Okay. So now let's look at these three terms closely, and then like we shall go ahead and construct the Bode plot of these three terms. So now, if we look at
sorry
these
to
three
interrupt,
terms,
sir.
and we, yes, please. Yeah.
So, actually, I don't know how I missed this. Actually, I didn't know that the lecture was gonna go for 2 hours. So I had a important meeting set up between 6 to 6:30.
Okay.
So I will need to attend that. It's very urgent.
Sure, please go ahead. Sorry, I could not inform you ahead of time because this was a, last minute changeover. All right. So please go ahead, attend that meeting. Anyway, I'm recording this video. I will upload the recordings in the Google Drive folder, right? And you can watch those videos later, and please contact me if you have any questions. Right, Aman?
Sure, sure, sir. Thank you.
Yeah, sure. Okay, thank you. All right. So let's go ahead. All right. So I hope it is clear how we decomposed into these three terms, right? If we look at the three factors, immediately we will see that P of j omega, right? We can write it as 0.1 and j omega plus 1 divided by 0.1 j omega plus 1. All right, so this is how we can rewrite what to say. We can write the sinusoidal transfer, right? So all right. So now going forward, if we look at the first term, so let's look at each term one by one. Okay, so let's call it as d1 of s. d1 of s is the first term is 0.1, right? So what do you think will be the magnitude and phase of this term? Magnitude will be in decibels, it will be 20 log 0.1, right? And what is this? What will be log of 0.1? It is
minus 20 log.
So
Zero.
this will be just minus 20 decibels, right? Right? Because a log of 0.1 is minus 1, right? So then we will have minus 20 decibels. Am I correct? Yeah. And its phase will be 0 degrees, right? Because this is a positive real number, right? So this is a, we have the first factor, right? D1 of. Okay. So the second factor, D2 of s, is going to be equal to s plus 1, right? So s plus 1 is going to be a first order factor whose corner frequency is what? What is going to be its corner frequency? So what is capital T in this particular case? If you compare it to Ts plus 1, what is capital T? 1, right? So what will be what? 1 by T? It will be 1, right? So because 1 by T is the corner frequency. So in this case, the corner frequency is going to be 1 radians per second, right? So that will be D2 of it, right? So this will have a high frequency asymptote with a slope of plus 20 decibels per decade. Please remember that, right? So here, the high frequency asymptote will have a slope of plus 20 decibels per decade. The low frequency asymptote will be the 0 decibel line, right? So that will be what to say? The facts associated with this particular factor, s plus 1. Okay? Yeah. So now, if you look at the third factor, D3 of s, which is 1 divided by 0.1 s plus 1, what do you think is the corner frequency? It is going to be 10 radians per second. Very good. Why? Because we compare it with the factor 1 by Ts plus 1, right? So we can see that capital T now is 0.1, right? So 1 by capital T will be 10, all right? So we will have the corner frequency to be 10 radians per second. So consequently, the high frequency asymptote will have a slope of minus 20 decibels per decade, right? So in this particular Okay, so these are the three factors, right? So that we will have. All right. So now, if we want to plot the Bode plot, see when I want you to plot the Bode plot using a pen and paper, you can just plot the asymptotes. Okay, that's fine. All right. So let's do it. Okay. So let us plot the Bode plot of the three factors, and then like we will see what we get out. Right. So let us let me draw the axis first. Okay, so this is the frequency. This is P of the magnitude of P of j omega in decibels. Now, how do I decide the range of frequencies? Please note that we have a corner frequencies at 1 and 10, right? So let's say we mark 1. Okay, I mark 10. Okay, and I can mark one decade lower than 1. Okay, which will be 0.1, and I mark one decade above 10, which will be 100. Okay, so like this I can mark. All right. So and the magnitudes, let's say I mark between what to say minus 20 to plus 20. Okay, so let us say this is plus 20. Let us say this is 0, and let's say this is minus. Okay, so let's start plotting each factor one day. All right. So first, let's start with 0.1. Right. So what is the magnitude of 0.1? It is a constant at minus 20. So we are going to have this to be the magnitude of 0.1. So let me write it. Okay. So this is the magnitude plot of 0.1. I'm sure all of us can agree to this fact. All right. Okay. So now if you want to plot the magnitude plot for S plus 1, what will I do? What is the corner frequency of S plus 1?
1 radian.
1 radians per second. And what do we know about the asymptotes of the factor PS plus 1? The low frequency asymptote is going to be 0 decibels. And what is the high frequency asymptote? It will have a slope of plus 20 decibels per decade. Right? So how can I plot it? What is 1 decade above 1? It is 10. So at 10, I should have a value of 20, right? Because at 1, I have a value of 0. If I want to have a slope of 20 decibels per decade, at 10, I need a value of plus 20, right? Isn't it? So only then we will have a slope of plus 20 decibels. So this has a slope of plus 20 decibels per decade. Okay, and consequently, this curve is the one corresponding to the magnitude plot of the factor S plus 1. All right, is this clear? So let me repeat. We know that if we look at the magnitude plot of TS plus 1, we know that the low frequency asymptote is the 0 decibel line, and the high frequency asymptote has a slope of plus 20 decibels per decade, right? So these are facts that we already are aware of. So that's all we used, right? So what we are doing is that like we plotted what to say 0 decibels till the corner frequency of 1, and then like we essentially had a high frequency asymptote with a slope of plus 20 decibels per decade, right? So this is S plus 1. Okay. So any questions? I hope this is clear. All right. So now let us move on to the factor 1 by 0.1 S plus 1, right? So for that, the corner frequency is at 10, and we know that anyway the low frequency asymptote is once again the 0 decibel line. So we have till 0 decibel, okay, till the corner frequency. And what will be the high frequency asymptote? It will have a slope of minus 20 decibels per decade, right? So how can I plot it? Any idea?
At 1 radians, it is minus 20 dB.
So at 100, it will be minus 20. That's correct. Very good. So at 100 omega equals 100, which is 1 decade above 10, I essentially take minus 20. I can draw a straight line, right? So consequently, this slope is going to be minus 20 decibels per decade, right? And this is the curve corresponding to 1 divided by 0.1 s plus 1. All right. So now what we do, we essentially add the three. Have we plotted all the three Bode plots? Yes. We have plotted the Bode plot for magnitude plot for D1, D2, and D3, right? As we know, we just need to add them, right? So why? Because if you go back, the magnitude of P of j omega is going to be the magnitude of 0.1, the magnitude of j omega plus 1, and then the magnitude of 0.1 j omega plus 1, right? So when we go to decibel measure, they just get added up, right? Because we are taking logarithm. So we need to add them, right? So can you help me in plotting the final Bode plot, of this factor? How do you think this will look like? So we can immediately see that at low frequency, the contribution will come only from 0.1, right? So till of course, once again, I'm not considering the actual curve. We are only considering actual curve. So till a frequency of 1, the magnitude will be minus 20. Does everyone agree? Because the contribution from the factor s plus 1 and 1 by 0.1 s plus 1 will be 0 decibels, right? So till the frequency of 1 radians per second, the contribution or the magnitude contribution will be only minus 20 decibels, right? So that will come only from the factor of 0.1. All right. Okay. So now what will happen? This factor will kick in, right? S plus 1 will kick in. So it will provide a slope of plus 20 decibels per decade, right? So what I'm going to have, from 1 to 10, I am going to grow by 20 decibels. So if I have 20 decibels, I come from minus 20 to 0, right? Because I am essentially going to have this plus 20 decibels per decade contribution from the factor s plus 1. Okay, so I hope it's clear how we got it. So this is going to be plus 20 decibels. All right. So as a result, we go from minus 20 to 0. But after 10, you see that 1 by 0.1 s plus 1 kicks in, right? And that will contribute a slope of minus 20 decibels per decade at high frequency. So the slope of plus 20 decibels per decade from the factor s plus 1 will cancel off, right, with the slope of minus 20 decibels per decade from 1 by 0.1 s plus 1. So consequently, what will happen? This will just flatten off at 0 decibels. Okay, so the red solid line is the magnitude plot of the transfer function which we have been given. All right, so it's a very simple example wherein we have plotted the Bode plot. Okay, so I hope it is clear, right? So how we got this, right? So essentially, what we will do is that, like, we will have the Bode plot or the magnitude plot of the sinusoidal transfer function P of j omega starting at minus 20 for low frequency till the corner frequency of plus 1, it will be at minus 20, and then after frequency of 1, the factor s plus 1, right, will contribute plus 20 decibels per decade. So the magnitude will grow at plus 20 decibels per decade, and from 1 to 10 we add 20 decibels, right, because that is the slope. So consequently, at omega equals 10, the value of the magnitude, right? So right, because the magnitude has grown by plus 20 decibels over a decade. So then what happens? Like beyond 10, the factor 1 by 0.1 s plus 1 will essentially contribute a slope of minus 20 decibels per decade. So the curve will flatten out, right? So P of j omega will have a slope of 0 decibels per decade, and that's how we get this plot. All right. Okay. Any questions on how we got this? Okay. So I hope this is clear, right? So this is how we got the phase plot. As I said, like if I'm asking you to draw the Bode plot by hand, it is enough if you draw the asymptotes. Okay, so that's more than enough. So now let us go to the phase. So as we know, the phase is once again going to be the sum of the phases, right? So it's going to be the sum of phase of 0.1 plus the sum phase of j omega plus 1 plus the phase of 1 by 0.1 j omega plus 1, right? So the phase of 0.1 is going to be 0, right? Because it's on the positive real axis, right? So the 0.1 will not contribute any phase. The phase of j omega plus 1 will be tan inverse omega. How do we get this? The phase of a complex variable is going to be tan inverse of imaginary component by real component. The imaginary component of j omega plus 1 is omega, and the real component is 1. So that's why we get the tan inverse omega. Then what do you think will be the phase of 1 by 0.1 j omega plus 1? It will be minus tan inverse of 0.1 omega. How did I get minus tan inverse of 0.1 omega? Because I have the reciprocal. So I have a negative, I get a negative sign. So I will have minus the phase of 0.1 j omega plus 1. And the phase of 0.1 j omega plus 1 is going to be tan inverse of 0.1. Right? So I'm sure all of us can understand how we got this expression. All right. So once again, what we do is that we just plot the three phases and then we add them. All right. So let's do the same now. So if we plot it, let me carefully plot the phase of the three factors. This is omega. This is the phase of P of j omega degrees. So let's use the same scale. So as far as frequency is concerned, so let's say we start from 1, we go to 10, then we go to 100. Let's say here we go 0.1, right? And phase, let's say we have go from minus 90, 0, and plus 10. Okay, so let me draw all these very clearly. Okay, so the phase of so I have drawn. Let me color code it differently. Sorry about that. I'm just going to draw those lines, and I'm just going to color code them differently. Okay, this is a horizontal line at 90. It's for our reference, and I'm going to draw a horizontal dashed line at minus 90. Okay, once again for our. Okay, so I'm going to use the same color code that I use for the magnitude plot. So let me use this color for the phase of the constant. So as we know, for the phase of 0.1, it is at 0 degrees, right? So we will have a horizontal line at 0 degrees. So this is the angle or phase diagram of 0.1, right? So what will happen to s plus 1? What is the phase plot of Ts plus 1? So if you recall, the phase will start from 0. It will go to 45 degrees of the corner frequency, and then it will go to 90 asymptotic. Right? The corner frequency is plus 1. So this will go to 45 at the corner frequency. So the phase plot is going to be something like this. It will go to 45, and then it will go to plus. Okay, so this is the phase plot of S plus 1. All right. So Then how do we plot the phase plot of 1 by 0.1 s plus 1? It will go from 0 to minus 90 degrees, right? And at a frequency of 10, it is going to have a value of minus 45. So the phase plot of 1 by 0.1 s plus 1 will be like this. So we are going to have something. Okay, so this will be the phase. Now the question is, how do we add them, right? Of course, the phase plot looks a little bit complicated, right? So than the magnitude plot, right? Because the magnitude plot, the addition was a bit simpler, but the phase plot, is going to be a little bit trickier, right? So why? Because we can see that you can have what to say. The phases starting from 0 degrees, right? For all the three factors, and the phase of s plus 1 going to plus 90 and 1 by 0.1 s plus 1 going to minus 90. So as omega tends to infinity, the plus 90 and minus 90 will cancel off, right? So if you look at the phase of P of j omega, finally it will go to 0, right? It will start at 0 and it will go to 0, right? So the question is, how does it vary in between, right? So please recall that the phase of P of j omega, as we wrote down previously, in this example, it's going to be tan inverse omega minus tan inverse 0.1 omega. Right? So that is what we have, right? So if I were to construct a very simple table in this regard, right? Plotting omega and P of the phase of P of j omega in degree. So we see that as omega tends to 0, the phase once again tends to 0. As omega tends to infinity, the phase tends to 0 degree. And then we will calculate the phase at the two corner frequencies, right? So one corner frequency is 0.1. So can you calculate what will be the phase at 1? One corner frequency is 1. So can you calculate what is tan inverse of 1 minus tan inverse of 0.1? So tan inverse of 1 is 45, right? So if we look at tan inverse of 0.1, I put, sorry. Tan inverse of 0.1 will be this, and I need to subtract 45 from this, right? So of course, it's the other way around, but then what I'm going to do is that I'll retain this and plus 45, but it will be plus 39.3, right? So this value is going to be 39.3, right? So that's what we get at 1. So at a frequency of 1, we are going to have a a phase of 39.3. In fact, if you calculate at a frequency of 10, once again we will have the phase to be 39.3. Okay, you can do that. It's going to be symmetric about that point, and so we are going to get something like this. So if we plot the phase plot, in fact, it will be having a shape something like this. Okay, it will reach a maximum in between the two corner frequencies, and at the two corner frequencies, it will have a value of 39.3. Okay, here also it's 39.3. Okay, and at this point also it has a value of 39. Okay, and this is the phase of the transfer function P of j. Right, so it's in the shape, so it will reach a peak between the two corner shapes. It is clear how we got it. So we can observe that for this particular transfer function, right? Note that the phase of P of j omega is always non-negative. Okay, is always greater than or equal to 0 for all omega. Right? So this is something which is very, very special about such transfer function. So in fact, the transfer function which I presented to you is the structure for a so-called lead compensator. Okay, I just wanted to inform you regarding this. Why it is called lead compensator? Because it is providing a positive phase, right, at all frequencies, or a non-negative phase at all frequencies, right? So that's why it's called as a lead compensator. So if you provide a sinusoidal input, what is going to happen is that like the steady state output will be leading the input that you provide, right? So as far as the phase is concerned, okay. So that's something which is interesting about this particular transfer function. All right. So I am going to leave you with a question in this regard. So as we observe, the phase essentially increases, then reaches a maximum and decreases, right? So what I want you to do is that like find the frequency at which the phase of P of j omega is maximum. Okay, that's point number one. Okay, and calculate the maximum phase. Okay, once you find the frequency at which P of j omega is maximum, you also calculate the value. Okay, of this phase. All right, so that's something which I'm leaving you as a exercise. So what you need to do is that like you need to look at this expression, right, and then work with that. Okay, so that's something which I want you to. Okay, so this is how we construct the Bode diagram of any given transfer function. So what we have done in this session is to essentially learn, like how do we break down a given transfer function into the building blocks that we learned, and then like we plot the magnitude and phase plot of the building blocks, and then like we essentially constructed the Bode plot. All right. So what I'm going to leave you as the next homework for submission, right? I think this is going to be homework number 4, right? If I'm not mistaken. I think this will be homework number 4. I want you to plot the Bode diagram for this plan transfer. Okay, S divided by S plus 1 times. Oh, sorry. Okay, so please plot the Bode diagram for this particular transfer function. Okay, then we will go from. Okay. So you can submit this not this Sunday, because you already I think have a submission due this Sunday. You can submit it next Sunday. Okay, I will anyway post it in the Google Classroom page, right, as far as this submission. Fine. Okay. Any questions on what we did in this session? All right. So if not, I will close this session and then we'll continue in the next session. Thank you.